Okay, so nice to meet you, everybody. So I'll start with a first slide to get you a first touch point on where the contamination actually is in the glass and what it actually looks like. So you can see that much of the CSP is concentrated always in the coarser fractions, where you can reach up to 15, 20, even 25,000 ppm. So 2.5% of the infill material in this fraction can be actually CSP, so ceramic, stones, and porcelain. But in these fractions, it's generally represented by a very few large objects. So these large objects are easy to detect and eventually easy to reject from our material flow. If we go then to have a look at the smaller fractions, we can see that the weight of the contaminations decreases and it reaches 3, 4, 5,000 ppm, depending on the country where the glass is collected and the collection point and the people behavior and so on. But the number of actually infusible pieces exponentially increases. And by the time we reach the very fines, so the fraction between 1 and 2 millimeter or the fraction between 2 and 3 millimeters, we see thousands of little fragments. Each of those can be a potentially defect in our customers, so in the factories where bottles are produced. Larger pieces are then usually easy to detect and eject, while the smaller pieces, they will eventually reduce the sorting capacity and the sorting efficiency of our machines. The effect of particle size distribution, it's very evident if we plot it against the sorting throughput in an optical machine. And you can see that in the very coarse fractions, so let's say if the pieces are bigger than 14 millimeters, it's quite easy to get very high throughputs in the area of 10, even 15 tons per hour on a single optical sorter. And the efficiency of separating these CSP pieces is very high, as you can see from the difference between the input stage on the first line of pictures and the output stage on the second line of pictures. Then if we move to the medium fractions, let's say around 6, 7, 10 millimeter in size, the efficiency that we get is still very good. You can see in the purple bucket, we just have a few CSP pieces after the first step of sorting, but the throughput is starting to decrease quite significantly. From 10 or 15 tons per hour, we move down to 8 or 6 tons per hour only on a single machine. Then by the time we go to the very fine fractions, the throughput is dropping to 1, 2, maximum 3 tons per hour. And we see also a decrease in efficiency. That's because the small pieces are harder to detect and even also harder to eject from the material stream. Also, we see the effect of starting with thousands of pieces of CSP in the input. Then, even if the efficiency is still maintaining 90, 92, 95% of efficiency, the output still contains many of those input pieces. Therefore, leading to a case where only one or only two steps of sorting are not necessary to provide a final product which is in spec for our customers. Therefore, more steps must be put in series to go to final quality. Then the big topic of today's discussion is the effect of crashing the glass before it reaches our recycling facilities. So, of course, like you say, Jean-Paul, in the introduction, the glass at a certain point in the production flow will be crushed, but it all depends on how it is actually crushed. So it's key that the glass is properly calibrated to ensure a good recyclability of the product. And in fact, the glass must be coarse enough that we can sort it easily, maintaining a high efficiency and high performance of our process, but not too coarse that we get clogging and pieces stuck inside of our optical sorters. So the glass is not just crushed in any way, but we use dedicated and specific machines to do the job. These are generally roller crushers, and we design them to apply just enough force, the minimum amount of force, to break the necks, the bottoms, very thick pieces of glass, which are the very strong ones that really needs to be crushed, but without wasting energy and without going to a full crushing where we break the weakest part of the bottles, for example, the body of the bottles. Also, we don't do an indistinct crushing on site, but we only crush what really needs to be crushed. So only the particles that are larger, for example, than 50 millimeter get crushed. What is already below this size is left untouched and will then eventually go directly to the optical sorting stage. This said, we see how compactors, shredders, plastic bag openers, and basically any other type of crusher that is not a roller crusher is creating an indistinct and uncontrolled crushing of the full fraction of glass. This will then generate an increased amount of fines, and an increased amount of fines will then lower the recovery of glass itself and therefore limit the recycling rate. So for sure, crushing glass will have a very positive impact on the upstream collection, because for sure the space that glass is occupying inside the truck or inside the bin is less, and then everything can be optimized. But then when it comes to the glass recycling facility, then we have an issue, because the finer the glass, the more waste we eventually produce. And of course, nowadays, where for the municipalities or private company, the glass is actually a product, it's not a waste anymore, it has also a value. But the value in a free market dynamics, it's given by the profit or the recyclability that company like Sibelco or other recyclers can get out of the glass. So a glass that is coming to our processes more crushed than usual could also limit the market value of the inbound material itself. Finally, a last slide from my side is about the current capabilities of the optical sorters. So in the past, it was common practice to sort glass down to 10 millimeters, then eventually down to 8, to 5, and so on. Nowadays, we are not limited anymore by the detection of the infusible particles, because if you take specific industries, such as the food, such as the seeds industry, they have machines that can go down to 1 millimeter, no problem. What is really mattering is the efficiency of sorting and the performance and the throughput that we can put in a given optical sorter. So we see that the number of infusible particles is very high in the fines. What does it mean? That for fine fractions, we need more sorting steps in series, because we need 1, 2, 3, or 4 steps to completely remove as much as possible all the thousands of pieces that we find in the input. But also, when we deal with fine fractions, we need more sorting width, meaning more machines in parallel. This is because we saw in the previous slide that in the fine fraction, the throughput capacity of optical sorters is decreasing, and then to perform the same job, the same ton per hour, we need more sorting width, meaning more machines in parallel. Also, when we're dealing with fine fractions, we see that it becomes difficult to sort paper from glass. Paper is normally sorted by means of air systems, so this can be suctions points, can be cyclones, can be blowers, can be air knives, but all of them, they exploit the difference in weight between paper and glass. However, in the fine fractions, and especially when the paper is wet, after having absorbed the humidity or the moisture or the water in general, glass and paper tend to have the same specific weight. And then it will be very hard to remove them by way of air cleaning. What does it mean? That we need to remove paper with the optical sorters. So we need to demand this task to the optical machines, which normally are only shooting out CSP. These machines, every time they are expelling an object, they are creating oversorting, they're losing glass. So if you can see in the picture on the bottom right of the slide, it's a nice example where to eject one piece of ceramic, so the red particle surrounded by green glass particles, the valves will open for 1, 2, 3, 4 valves in series for a certain period of time, which is the vertical arrow. And just to hit one ceramic piece, we will discard all the glass pieces around. So for every fine piece of ceramic that we hit, we might be losing 10, 15, 20 pieces of glass around it. So in conclusion, the higher amount of fines that we see in our plants will give us an increase in capex because of more sorting power is needed in our plants, an increase in opex because of additional running cost, for example, the compressed air to shoot them out and the maintenance and so on, but also a higher oversorting leading to a high waste cost because some of the particles of glass will be expelled with the fine CSP and eventually exit the glass loop.